Let's take a look at matrix solution of linear systems. First, let's define what we mean by a matrix. You probably recall matrix from your intermediate algebra classes. Just a reminder, what is a matrix? For us, it's simply an array of numbers. An array is a listing of numbers. That's what it is. So if every matrix, let me just create a generic matrix here. Every matrix is made up of rows and columns. So for example, I'm just making this up, 2, 3, 4, negative 1, 0, 5, and 2, 5, 7. So this is a matrix. Notice we have square brackets, opening, closing brackets. And then we have just a listing of numbers. The anatomy of the matrix, the rows of the matrix, we count them from top to bottom. First row, second, third, top to bottom. The columns go from left to right. Column 2, column 3, column 1, 2, 3, from left to right. Every matrix has a dimension or size. The size or dimension of the matrix, or the order of the matrix, is the number of rows by columns. It has to be in that order, by the way. Rows by columns, short for columns. So this one has 3 rows, 3 columns. Another one, for instance, if I have 1, 2, 3, this one has 3 rows, 1 column, right? So the order or dimension of this matrix is 3 by 1. Notice that 1 by 3 will be a whole different matrix, right? There you go. That's a 1 by 3. So that's what I meant. It makes a difference how we write the size or dimension, whether you write row first, column second. It has to be rows followed by columns. Okay. Now, it turns out that we can actually write systems of equations using matrices, and that's what we would like to do, and then solve them using elimination method. So for instance, let's say I'm going to make up an example of a system, a simple linear system, 2 equations, 2 unknowns. There you go, 5x plus 2y. The numbers don't matter at this point because I'm not going to solve this one. So we can rewrite this as a matrix. The matrix is going to have the coefficients 3, negative 4, 5, 2, and then the constants 1 and 9. So notice we basically strip the system from the variables and the equal sign. Now some textbooks actually put some kind of a dotted line here to separate the coefficients from the constant, and they call this the augmented matrix. The augmented matrix. And how was it augmented? The presumption is that I had, let's say, 3, negative 4, 5, 2, and then I augmented it with the constants. So that's where the name augmented matrix comes from. Okay. And let's see how this is going to help us with systems. Well, for example, if I have, remember these are coefficients on x and y, these numbers in the first 2 columns. So for instance, let's suppose I have a system that looks like this, 1, 0, 5 and 0, 1, 7. So if I write a system or an equation corresponding, let's say, to the second row of this matrix, this will read as 0x plus 1y equals 7, correct? Of course, 0 times anything is 0, 1y is y, so y would be 7. And there is a solution for y. Same thing for the first row, 1x is equal to 5, so x is 5. Because 0y, we don't write it. Therefore, you can seek the appeal of the matrix. Then if we can get the matrix in a specific form that you're looking at using these 1s and zeros, then we may be able to actually write the solution to the system. All right. Now, let's say in this section, we're going to talk about the echelon form of a matrix. Remember, an echelon is like staircase formation. A matrix is in echelon form in the case of 2 equations and 2 unknowns. If it's in the form like this, this is called the echelon form of a matrix. Okay, and here's the staircase, the steps like that. That's what makes it echelon. So there's the echelon form of a matrix that has two equations, two unknowns. The echelon form for three equations, three unknowns is going to look like this. So it's going to be A, B, C, D, E, and F. The A, B, C's here are numbers. And here's again the staircase formation here, which cause them to call it echelon form. Now it's important to have ones on this, what we call the main diagonal. This is the diagonal of the matrix, not for the matrix of coefficients, that is. There you go, that's this diagonal. So the matrix that has ones along the main diagonal is said to be in the echelon form. Okay, now we can go further. Notice in echelon form, by the way, this one, it says Z is equal to F, but then it doesn't say Y is equal to a number. It gives you Y in terms of Z, right? Gives you X in terms of Y and Z. So the echelon form helps us solve for the last variable, and then we can always back substitute and solve for the other two variables, if this is three equations, three unknowns. The other form of the matrix that is very useful to us, not the echelon form, but it's called the reduced echelon form. The reduced echelon form is actually when you get not only zeros below the main diagonal underneath the ones, you also have 0 above the 1. And then let's say here I have A, B. These are just numbers now. And it is in this form, let me, instead of A, B, call them, I don't know, I and J, something like that, IJ. And it is in this form that we can identify, we say, oh, okay, then Y is J and X is I. There you have it. In the echelon, reduced echelon form. That's the advantage. What does the reduced echelon form look like for a 3 by 3? Again, you have ones below the main diagonal, correct? I mean, ones along the main diagonal, 0 beneath it, below it. You have this nice triangular formation of zeros. Okay, and then you have those zeros above the main diagonal also. And these would be, let's say, I, J, K now, just to be different. Or we can call them ABCs, don't matter. And those are the numbers. So for this one, looks like Z is K, Y is J, and X is I. So we have the solutions in the reduced echelon form. Now, in order to go from the original form of the system to the echelon form, we're going to go through a process that is called Gaussian elimination. Gaussian elimination. And we'll do that in just a moment. And in order to go from echelon to reduced echelon form, then we use what they call the Gauss-Jordan elimination method, named after Carl Gauss, and Gauss-Jordan elimination method. So that's how we get it in the reduced echelon form. Remember, the key difference between echelon and reduced echelon is that the upper, it's the upper formation of zeros. There, this one, where you don't have that in the echelon form. So that's the key difference between echelon and reduced echelon forms. All right, so let's see how this is going to work. Well, in order to do this, we need to have a set of rules on how we can transform the matrix from its original form to either echelon form or reduced echelon form. So let me bring those up here for you. And there we have it. This is called matrix row transformation, or operation on matrices. Some books call it elementary row operations. And you probably heard me in the previous section referring to systems of equations, to the individual equations as rows. So this is what I was thinking. It is okay to think of each equation as a row now in a matrix. So these three rules, you've actually seen those before in the previous section when we talked about elementary operation on systems. Now, same operations hold for matrices. Remember, these are row operations, okay, not columns. We do not have column operations, but we have row operations. First one, you can swap out rows. Let's swap in the equations. Multiply, divide elements of any row by a non-zero real number. That's just multiplication rule of equations. And finally, replace any row by the sum of the elements of that row and a multiple of another row. Okay, and we will do that, and you will see how this is done. So let's actually do an example where we want to use Gauss-Jordan elimination to solve the system. So my example, I'm going to have, let's go with 6x negative 3y minus 4 equals 0. And the other one would be 3x, let's go plus 6y minus 7 equals 0. Now, it's important. It's very important that we write the augmented matrix correctly. In order to write the augmented matrix, the constants before we write the matrix should be on the other side. Okay, so I'm going to move the constants first of all to the other side, and there. Now I have it in standard form, and now I can write the augmented matrix. So it's a little tricky. I could have done it from the get-go, but if I did, then you wouldn't, I would have to explain why this is a 4 where that's a negative 4. You see that? It's because we look at the augmented matrix. All right. So if we can get past that, then we're all good. So here's the matrix form of the system. Now, using this set of rules, remember, I can swap out the rows of a matrix. I can multiply any row individually by any non-zero, and if we need to replace a row, we can do that. The row you want to replace it, some of the element in the row that you can add, some means you add the row that you want to eliminate with a multiple of another row. Okay, so I'll show you how this is done. So let's actually solve this one. And I'll write this set of instructions as we do this. So for example, I'm going to switch the first and the second row. So I'm going to go R1, the double-headed arrow, R2. That's what I just did, or I'm about to do. So I'm switching the rows of the matrix. Now, why would I want to do that, right? You don't have to. I just want to show you the operation. And now I can actually use this row to create a 0 underneath it. Now, we did mention that you gotta have 1, 0, 0, A, B, C like that. But it's okay for the work that we do if we don't have ones along the main diagonal. In other words, I'll show you what I mean in a moment. Well, that's fine. So let's say I want to eliminate this element now. Going off the pattern, I need to have a 0 here, right? The echelon form. That is not optional. I have to have a 0 there. But the 1 and the 1 here are somewhat optional in the work that we do, because we can still solve them without them being 1s. So here we have it. We have 6. In order to get rid of 6, remember, I need opposite of 6, which is negative 6, so they add to 0, and that's what we want here. So I'm overlooking everything here. I'm not looking at these. Okay, we're just looking at 3 and 6. What would it take to create a 0 in that 6? Well, we need help from the first row, because I cannot multiply by 0. If I do, that whole row will eliminate. The rule number 2 says we can multiply by non-zero real number, not 0. Okay, so let's multiply the first row by negative 2 times first row and add it to the second row. That's the row we want to get rid of. So I'm doing the sum of the row I want to get rid of and a constant multiple of another row. That's what I'm doing, number 3 of the operations. Now, when you do this, because I'm changing or replacing the second row, therefore the first row is intact. the first row is not going to change through this process. We call this first row a helping row, actually. It's simply going to help us get rid of another row and replace it. In the process, it's not going to replace itself. Okay, so what's going to happen here? Negative 2 times row 1, that's negative 2 times 3, negative 2 times 6, negative 2 times 7. Then we're going to add it to the other one. And adding columns, negative 15, negative 10. And the new and improved row, row 2, is 0, negative 15, negative 10. All right, so notice we took the first step, created a 0 there. And now moving on, at this point, by the way, at this point, we could solve this, we can solve the system, because this row reads negative 15y equals negative 10, and y would be negative 10 over negative 15, which is 2/3. You see that? So we can solve it. In fact, that is a solution for it, right? But let's do this to where we get the echelon form. So I want to actually create the ones here. So let's see how we're going to create the ones here. Well, first row, I'm going to multiply by 1/3, row 1. 1/3 times 3 is 1. So you multiply entire row by 1/3. So 1/3 of 3 is 1, 1/3 of 6 is 2, 1/3 of 7 is 7/3. And there we have it. Now, I need to, so I have the 1 here. I need to get a 1 in the second row in that key spot. Right now, there is a negative 15. True? So how am I going to get that to become a 1? If you need to create ones, not zeros, chances are you use rule number 2. Okay, so to change into 1, likely you have to use number 2 of the operations, elementary row operations, this one. You have to multiply or divide by something. To replace, that is to create a 0. To create a 0, you need to use number 3 of the operations. You need help from another row. Okay, so I need to create a 1. Well, to create a 1, I need to multiply that row by something, by reciprocal. So I'm going to go negative 115 to row 2. Negative 115 times 0 is 0. Negative 115 times negative 15 is 1, right? And negative 115 times negative 10 is 10/15. Correct? And we have the matrix. This is now in the echelon form. You see that? Because we have, again, this triangular formation where you have 1 on the main diagonal, 0 below the main diagonal, echelon form. Once we have the echelon form, from the second row, y is equal to 10/15. Divide the 5s out, we get 2/3. There. And once we have the solution to y, we can back substitute in the first row, x plus 2y equals 7/3. So x would be negative 2 times y. I'm moving y to the other side. So it's going to be negative 2 times 2/3 plus 7/3. That's negative 4 plus 7/3, or 3/3, or 1. X must be 1. The solution is 1, 2/3. And the system is solved. Okay, now we have the solution, but let's actually go and take this a step further. Let's go to the reduced. Let's say we want to do reduced echelon form. And the process that we just did, by the way, what we did here, this is called Gaussian elimination. Now, we're going to create a 0 above the 1. True? Right now, there is a 2 there. We need to make that into a 0. So, we need help from the row below. We're going to leave the second row now intact. And I'm going to rewrite 10/15 as 2/3. Is that okay? Because we just resolved it here. That's what that is, 2/3. Now, in order to create 0 directly above it, right now there is a 2 here. We need a -2. So let's do -2 times row 2 added to row 1. -2 times second row, that's -2 times every one of these. So that's going to be 0, -2. -2 times 2/3 is -4/3. Okay. We're going to add it to existing first row. Existing first row is this row. All right. And that row is 1, 2, 7/3. We're going to add them. So we're going to get 1, 0. 7/3 minus 4/3 is 1. So this becomes 1, 0, 1. And see how the transformation worked. And now we have this nice pattern of 1s on the main diagonal and 0 on the off diagonals. And at this point, we're going to call that x is 1 and y is 2/3. And there you have it. The solution to the system by using, just making this 0 above the 1. You add another name to the name Gaussian elimination. This is what the Gauss-Jordan elimination does. And there you have it. So the system is solved. Okay, pretty easy. Again, it's just the arithmetic of this thing that you got to be careful when you add, subtract, multiply, and divide. Now for 2x2, this isn't bad. 3x3s will take longer to do. So I'm going to do an example of a 3x3 with you, where we just do a row echelon form, not reduce, because it will take too long. Okay. And now going forward, by the way, we're not going to be doing this because it just takes too long. So we use either elimination or substitution. Well, most likely elimination method to solve systems, not this. All right, so here's my 3x3 now. 3 equations, 3 unknowns. Equals -13. And we want to solve this using Gaussian elimination. That means I need to go to row echelon form. First of all, I need to write the matrix, the augmented matrix. Remember, make sure the equality, the numbers are on the right side of equal sign to write the augmented matrix correctly. So that's 1, 1, -5, -18. And then I have 3, -3, 1, 6. Then 1, 3, -2, -13. All right. And there is the augmented matrix. Now we need to proceed. The final product for us we're looking for is this 1, 0, 0, 1, 0, 1, number, 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 like that. Okay, so this is the pattern we're looking for. Now, as far as how we're going to create this, usually what we do, this is the path that we choose going through this process. You get your, what we call the leading one here. Okay, it leads to the future operations on the matrix. And then we try to get a 0 here, a 0 here. Then we go across, try to get a 1 in that position, move below, get a 0, and then cross over to get a 1. So that would be our path through the matrix. Okay, now with that in mind, let's do this. I already have my leading 1 in that key spot, right? So moving along the arrows here. Okay, I need to create a 0 below the 1. Right now there is a 3. Again, don't look at anything else here. Don't look at anything there. How do I get a 0 there? Well, I need a -3. That -3 has to come from the first row. So I'm going to do -3 times first row added to the second row. All right. Now remember, first row is the helping row. It's going to help me achieve what I like to achieve here, which is to get a 0 in that spot. So I'm not changing those numbers. So I went ahead and rewrote the numbers in the first row. Now, negative 3 times first row, I'm going to multiply negative 3 times every element of that row. So it's going to give me negative 3, 15, and negative times negative is positive 54. Okay. We're going to add it to the existing second row. 3, negative 3, 1, 6. And when we do that, the numbers are 0, negative 6, 16, and 60. That becomes the new second row. 0, negative 6, 16, and 60. Okay. Moving along the arrows. Next, I need to get the third row, first column element entry to be 0. What is it right now? There is a 1 right now. How can I make it a 0? Let's do negative 1 times first row, add it to the third row now. Negative of the first row, so that would change all of those numbers to negative numbers. Negative 1, 5, 18. And we're going to add it to the third row. The existing third row is 1, 3, negative 2, negative 13. Add, we get 0, 2, 3, 5. 0, 2, 3, and 5. And check it out. We got the 1, 0, 0 pattern. Let's create a 1 along the main diagonal in the second row. Right now, there is a negative 6 there. So I could divide by negative 6, right, to create that one. Okay. Or if we wanted to, remember, this is recommended, but we don't have to do it exactly that way. And the reason is this, because I can see that I can create a 0 actually relatively easily here, right? Either do, if I do 3 times 2 added to negative 6, I can get a 0 there. All right. So what do I want to do then? Let's, at this point, let's do this. Let's multiply 3. This is what I'm going to do. I'm going to do 3 times row 3 added to row 2. This time, 3 is the helping row, right? Multiplying it by 3 and adding it to the row I want to get rid of. First row doesn't change. Third row will not change either, because that's my helping row. It's the second row that's being manipulated. 3 times third row, that's 3 times 0, 3 times 2, 6, 3 times 3, 9, 3 times 5, 15. Existing second row, 0, negative 6, 16, and 60. And then add them, we get 0, 0, 25, 75. 0, 0, 25, 75. Okay, not bad. And then what do we want to do? Let's say we're going to now make a switch. I'm going to swap out row 2 and row 3. See, I'm staying within the confines of the elementary row operations, doing operations that are legal. Switch the rows 2, 3, 5, and then I have 0, 0. And at the same time, well, let me do it another step. Don't want to do too many steps in one. Okay. So notice I have that lower triangular formation, right? I just need to make these ones, correct? So at this point, let's do third row by divide by 25 times third row. So that's going to be 0. 1/25 times 0 is 0, times both 0 is 0. Oh, that's interesting. Looks like a happy face, doesn't it? Huh. It's happy because we got the zeros in the right spots. Okay, 1/25 times 25, those are reciprocals multiplied to 1. 1/25 of 75 is 3. And there we have that one. First row, 1, 1, negative 5, negative 18. Now, the existing second row, just so you have it in one more step. Oops, didn't mean to do that. That's 2, 3, 5. We're almost there, right? Remember our pattern 1, 0, 0, 1, 0, 1. I just need a 1 there. So let's multiply now second row by 1/2. So I'm going to go 1/2 R2. First row 1, 1, -5, -18. Second row 0. Half of 2 is 1, half of 3, 3/2, half of 5, 5/2. And finally, the third row is going to be 0, 0, 1, 3. Perfect. And we got this down. So now I have truly the echelon form. We got our 1s on the main diagonal and 0s below it. Now, with this, I should be able to now solve this system, correct? The third equation, the third row, reads z is equal to 3. Now we can back substitute in the second one. The second one says y plus 3/2 z is equal to 5/2. Well, z is 3, right? So that's y plus 3/2 times 3 equals 5/2. Subtract 3 times 3/2 is 9/2. So subtract 9/2 from both sides. That gives you -4/2, which reduces to -2. Therefore, y is -2. And what is x? Well, the first row reads x plus y -5z equals -18. And that would be x. -2, -5 times 3 equals -18. 5 times 3, 15, and 2, -17. So I'm going to add 17 to both sides, and that will solve for x. Therefore, x is -1. The solution to the system is -1, -2, and 3. There you have it. And again, just want to emphasize that we have this nice triangular formation, which you have 1s along the main diagonal and 0s beneath them. All right, so we're done with this example. Let's take a look at another example. Now, here's an example where, like, well, what could go wrong? Well, not necessarily go wrong, but what else could happen when I do this? What if the system is inconsistent, for example? How would that show up in the matrix, right? So this system that I'm writing, and we don't know whether it has a solution or not, so we'll see. So this is actually the system. And then I have -6x, -10y, plus 2z equals 0. All right, let's solve this one. First, the augmented matrix. It's going to be 3, 5, -1, -2, then 4, -1, 2, 1, -6, -10, 2, and 0. Correct? There's the augmented matrix. So for this one now, let's multiply. Let's say I want to get a 0 here in that spot. So I'm going to do 2 times row 1 added to row 3. First row, intact. Doesn't change. Second row, no changes there. And the third row, well, 2 times first row, that's 2 times 3, 6. 2 by 5, 2 by -1, 2 by -2. Added to -6, -10, to 0. Opposite, 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 and that's -4. So the new third row reads 0, 0, -4. And check this out. In the third row, we have zeros on these are the coefficients on x, y, and z, correct? Remember where the system came from initially, based on x, y, z. So this one just says, or reads, 0 equals -4, which is, of course, again, it's not true, even on a good day. So because this is a false statement, right? False statement, therefore, the system is labeled as an inconsistent inconsistent system, and therefore there is no solution there. No solution to this system. So this is what could show up as we try to do these systems. And finally, let's do an example of a matrix here. And suppose we want to solve and actually write this in, let's go to maybe reduced row echelon form on this one. Okay. Yeah, let's use there you go. Suppose I'm giving you now the matrix form like that. So we have the matrix form, and the variables here, because I have two equations, two unknowns, are x and y. And let's say we just want to get the substitution method going here using back substitution to solve the system. Remember, the second row means y is 3. The back substitution, x plus y is 5. X plus 3 equals 5. So x is 2. Well, pretty easy. There you have that one. And if I just want to create, this is in echelon form, let's make it the reduced echelon form. If I want to write it in reduced echelon form, then I just need to create a 0 above that, right? Well, I'm going to do negative R2 added to R1 and replace R1. Negative R2, that's 0, negative 1, negative 3, right? Negative of every element in the second row. The existing first row, 1, 1, 5. And so here's my second row. I don't want to change it. And my first row is going to be 1, 0, 2. And there you have it. I have it now in reduced echelon form. The first row reads x is 2, the second y is 3. Again, going forward, we're not gonna be doing a lot of this, especially 3 equation, 3 unknowns. But this is a passing section. We had to talk about it because that's all there is in this section. All right, so we're done, and thank you for watching.